So, welcome to the final lecture in the Solving Unusual Maths Problems series. I've entitled this one MAT2, which is a little misleading because there's going to be a large number of questions from what's called the TMUA. Okay, so I'll explain a little bit about that first. Okay, so this is taken at the same time as the Oxford MAT, November of year 13, and you're encouraged to take it by a number of universities for mathematics or mathematics related courses. Now here's a list of the universities at current, and this is a growing list. Okay, it's quite a new qualification, this one. It's only going for sort of 3-4 years. So here's a list of the universities that accept it. Now the big difference with the TMUA is you sit it, but you don't have to reveal your results to the universities. It's up to you. So you can take it. The results come back quite fast, actually, just about 3 weeks. And then you can decide whether to reveal it to your universities or not. Now, if you have a good grade and you reveal it to the university, they will often give you a lower offer. So it's not usually included in your offer. You don't have to pass TMUA or get a certain score in TMUA. But if you do get a good score in TMUA, they may well reduce your offer for your course. Okay, so it's 2 papers. In effect, is one. They're taken consecutively, so you have a brief rest between them. Anyway, they're 2 1.25-hour papers, each comprising 20 multiple choice questions, and again, they're non-calculator. Now, the difficulty of these is it's not the same level as MAT and STEP. It's a little bit lower than that, but it's certainly a good stretch from A level. So it's really good practice for MAT anyway, and in of itself it's quite a nice level to aim at. So here is the first of the TMUA questions. So it's a question about integration, and if you notice, each of these looks like a graph transformation, possibly, and indeed that's probably the best approach to take. So you've got to choose which of these must be correct, which of these 6. Okay, I'll leave you to it now. Now, each one of the answers had an A in it. An A is the integral between 2 and 4 of f of x. We've got f of x plus 2, which is f of x translated left by 2 units. So here's the original area we want, and here it is transformed left by 2 units. So now you can see the integral between 0 and 2. So we certainly want an answer with the integral between 0 and 2 in it. That will give us the A. Then, of course, we've got the plus 1 to integrate. And fairly obviously, plus 1 integrates to give between 0 and 2 gives you an answer of 2. So combining those two, we get an answer of A plus 2, which is B. Now, an alternative approach is to shift the whole curve up by 1 unit. Okay, so you've sort of got a curve that looks like that now. Now what will happen is you'll end up with a rectangle underneath the area that's shaded in here. You'll end up with a rectangle underneath it with width 2 and height 1, and that of course has an area of 2. So we can also get the 2 here from thinking of moving the graph up by 1, and what area would we trap underneath the extra part we've just produced. So another TMUA question, this time a binomial expansion. Now this is the sort of thing you might get in an AS paper, but it's a little more involved. Okay, so have a go at this one and we'll look at the answer shortly. Now we could use Pascal's triangle to get the coefficients and then expand it in the standard way we've learnt in AS. But there are 6 terms here, And really, I'm only interested in the x to the 4 term and the x squared term. So there's a much more elegant way of picking out particular terms, which you may have covered yourself. So we want an x to the 4 term. And of course, if there's an x to the 4 term, the product with it must be the bx to the 1 term, because the 4 plus 1 gives you 5, which is the overall power. And now to find the coefficient, we use 5 choose 4. Now, you can use either power, it turns out. 5 choose 4 or 5 choose 1 will give you the correct answer. Okay? Now we'll do the same thing here. And there's the x squared term. Now, you've got to know the formula for these choose options. You haven't got your calculator in the test, so you've got to know that 5 choose 4 is 5 factorial over 4 factorial 1 factorial. However, with your practice, you notice that a lot of these cancel down quickly, so that'll cancel down to 5, for instance. And the 5 choose 2 is 5 factorial over 3 factorial 2 factorial, and a lot of it cancels down. Okay, so there are little tricks there you need to learn. But once we've got these two, we can do a further analysis. And here we go, in a little more detail. So here's the term we use, tidied up a bit. 5ab 4x to the 4. And here's the other term, 10a cubed b squared x squared. Now it's the coefficients we're interested in. Remember, one coefficient is 8 times the coefficient of the other. So there's one coefficient. There's the other coefficient. And now we're making one 8 times as big as the other. Okay? Divide through. And as it mentions, a and b are both positive. We can take square roots then. So we've got b squared is 16a squared. Square root both sides. You don't have to worry about the plus or minus. And you get b is 4a. Now they've got to be positive integers. Okay, and they want the smallest possible value of a plus b. Okay, so we just want those to be the smallest values we can think of, where one number is 4 times the other. And 1 and 4 are the obvious candidates. Okay, so make a equal 1, b equals 4, a plus b is 5, and option C is the answer. Okay, so another TMUA question. This time it's a question about integrals and summation. So if you look carefully, we've got an integral defined in terms of n here, and then we're going to have to add up lots and lots and lots of those integrals, to be precise, n of those integrals. So again, pause here, have a go yourself, and then we'll have a look at the solution. Okay, well let's look at the integral first. It's a fairly straightforward integral, as you can see. N minus x shouldn't be a problem. Plug some values in, and we get half n. There's an alternative way of looking at this. If you've got the line y equals n minus x, you could sketch that and have a look at the area under that. Most students would prefer not to do this, but if you have a look, it's actually very pretty, very simple.
Has a gradient of -1, so it crosses the x-axis at n as well. It doesn't take long to work out the area of the triangle is 1/2 n squared, which makes fx a half n.
Well, that's g of n. It's the sum of all the different integrals going from 1 up to n. And we found out the value of the integral is half r. And we can take out that half when it's a summation. Every term is half times something plus half times something plus half times something. So in other words, it's half of all the somethings added together here. So you can take that half out. That's not a problem. Now, this is a result you're expected to know in effect. Okay, if you sum all the numbers from 1 to n, you end up with half n brackets n plus 1. Okay, the summation is actually the triangular numbers, it turns out, that formula. And the other thing to think about with this is it's a arithmetic series. If you've covered those, okay, there's another way of deducing it. But anyway, this is a result you're expected to know. Okay, so we want to sum half, or rather the sum up to r is half n plus 1, and of course we're timesing that by a half. So g of n turns out to be a quarter n. n plus 1. Now, the question asks us, when is this g of n above 150? So it's probably better to multiply out, okay, the quarter, and so we've got n plus 1 is greater than 600. Now we're looking for integer values, so probably the best thing to do here is a bit of trial and error. Now hopefully you've got enough feeling for multiplication to realise the sort of numbers we're talking about. 30 times 30 want to be 900 odd, 20 times 20 want to be 400 odd, so we're talking about somewhere in between that. So the best thing to do is just try out some numbers until we get the result that produces a value over 600. And if you try 24 times 25 you get 600 exactly, and 25 times 26 it does jump above 600, and it's a strict inequality, so we need that value there, the 650. So n is 25, which is answer D. Okay, so another TMUA question, this time about quadratic inequalities. And what we're doing is we're comparing one quadratic inequality, the top one, with this quadratic inequality here. Okay, so I'll leave you to that if you pause for a bit, and then we'll have a look at the solution. So it's a happy quadratic. We've got roots p and q, crosses the x-axis at p and q, and as it says, we know c is less than 0, so it's going to cross the y-axis at a negative value below the x-axis. So there's the inequality, and as of course you know with quadratic inequalities, as it's less than 0, we're talking about this region here. So a set of values on the x-axis are between p and q. So they're the original solutions. Let's shuffle that graph into the corner. Now let's look at the more complicated quadratic, the second one. So we need to find the roots of this quadratic in order to look at the inequality. The only way we can get these roots is by using the formula. So we sub it in with a is 1, b is bc, and c is c cubed. So this can be confusing. Often better to use capital A, B, and C if you're going to write them down. To distinguish, but anyway, it's the quadratic formula. If we tidy it up a little bit, we get half c brackets minus b plus or minus the square root of b squared minus 4c. Now notice that little trick there. We've taken the c out from both terms, and when you take it outside a square root, you have to take the c squared out. Okay, but that does tidy it up a great deal. Now that's particularly useful because if we go back and look at the original quadratic and solve it using the formula, we get this set of values, or this pair of values rather. Now comparing the two, you'll see that taking the c out was the master stroke because they're just a multiple of one another, or rather the roots of the second are a multiple of the roots of the first. Okay, so it's got to be PC and QC, we've clearly multiplied by C. Now, subtle though, it's got to be in some order. We can't assume that PC and QC are in the same order as P and Q. It depends on whether C is positive or negative. Let's look at that in a bit more detail. As I said, PC and QC are the possible solutions. We've got C or D here. In one it's PC, between PC and QC, in D it's between QC and PC. Well, the point being, C is less than 0. That was part of the question. And since P is less than Q, multiplying through by negative, we reverse the inequality. Okay, so in fact it's Q that comes first, or rather QC. So D must be the answer. Now there's an alternative, rather elegant method of producing the correct solution, which I have to admit I didn't spot, which is to do with dividing through by c squared, which is clearly positive, so the inequality remains the same. And if you tidy that up, you'll notice that x has been replaced with x over c. So if the original inequality has x replaced with x over c, we can replace the solutions, replace the x in the solutions with x over c, fiddle around with it, and you get the solution, the required solution, fairly quickly. So it's a very elegant way of doing it, but it's not one I suspect that most students would come up with themselves, particularly under test pressure, but it's a lovely way of doing it. So another TMUA question. This one, straight lines and geometry, so freeze and have a go yourself. So we need a nice diagram for this one, and the question is all about finding the area of the rectangle there. Okay, so the first thing we can do is find the length of PQ. Simple bit of Pythagoras, and we get root 5. Now slightly more difficult is the length of QR, okay, because we don't know what R is at the moment. However, it's a rectangle, so PQ and QR are perpendicular. So we get gradient of PQ is 2 and gradient of QR must be minus a half. Okay, now the gradient of QR can also be written in this form using the points QR, and if we rearrange that, we get R is 17. Okay, so now we have the coordinates of R, 17, 0, and we should be able to find the length of QR. Again, using Pythagoras, and we get a value of 8 root 5. Now we've got the two, the length of PQ and the length of QR, so it's now simply a matter of multiplying the two together. Root 5 times 8 root 5, and from that we get 40, which was E. So I want to introduce you to a well-known problem. It's called the, unsurprisingly maybe, 4-card problem. And you can read it underneath, but there are 4 cards, number on one side, colour on the other. And the question is a logic puzzle. Which cards have to be turned over to check that if a card shows an even number on one face, then its opposite face is red. So have a quick go at that. And here's another problem. Again, you can read it. 4 people in a pub, each represented by a card with an age on one side and a drink on the other. And the question this time is which cards or cards must be turned over to test the idea that all 4 of them are drinking legally. Okay, so have a go at that one too. Now let's get back to the original problem. Now, I'm suspecting you may have found this one a little more difficult, so hopefully you got it right though. Clearly, you have to check the 8 to see if it's red on the other side, okay? But the other one you have to check is perhaps counterintuitively the brown card, okay? You've got to check the brown card to check there's not an even number on the other side, because if there were an even number on the other side, it would have had to be red, okay? And clearly it's not, it's brown, okay? So those are the 2 cards you need to check. Obviously you don't need to check the 3, okay, because you don't care what's on the other side. It's a question about even numbers. But you also do not need to test the red one, okay, because it says if an even number is on one side, red must be on the other. But it doesn't mean that if there's an odd number on one side, it shouldn't be red on the other. So the red card does not need to be touched. Okay, and that's the mistake that most students make. Now, moving on to the drinking question. This one, most people tend to find much easier. Which ones do you need to check? Well, clearly you need to check the 16-year-old. Are they drinking beer? Turn over the card. And also the beer drinker. Are they under 18? Turn over the card. You don't need to check with the person who's drinking soda, so they've got it there, and you don't care about what the 25-year-old is drinking. Now, logically, these two questions are equivalent. The one I showed you before and this one. Okay, they're exactly the same question, just one's a lot more wordy. And what it tends to show is that humans are pretty good at this sort of logic puzzle, provided it's put into a context they understand. Okay, so this sort of thing we think about every day. We're used to this sort of idea of testing things out, but when you do it just with pure numbers or numbers and colours and that sort of thing, we tend to psychologically just be not as sharp at getting through into the question and seeing what's going on. So I want you to bear this in mind, because these sort of questions coming up now, I'm going to give you a couple of logic questions, and one first of all and one later. And they're a little more difficult with maths, and you really have to pay attention, particularly to the problem we have with not spotting the brown card had to be turned over. Okay, it didn't seem to be part of the question. It wasn't mentioned. You know, if it's even, it has to be red. Okay, but you have to check the brown card. Okay, in that sort of context. And we've got the maths ones coming up, and let's have a go at a pair of them. Okay, so here's a very mathsy version, in effect, of one of those card problems. So we've got three statements, which you need to read carefully, and then beneath you have one result, that 91 is 7 times 13. Now the question is that a counterexample to any of those three? Bear in mind, none of them is a possibility. Okay, so maybe it doesn't work for any of them. So let's look at them. Let's look at them in reverse order. So number 3, no multiple of 7 greater than 7 is prime. Okay, now if you think carefully about this, clearly no multiple of 7 greater than 7 is prime, because it would be 7 times something. 7 times 2, 7 times 3, 7 times 4. They can't be prime. So statement 3 is true. We're not going to find a counterexample to that. You don't even have to look at what the possible counterexample is. It's true, so you don't need to even look for a counterexample. So that's 3 gone. Now let's look at 2. Every prime greater than 5 is of the form 6n plus 1. Well, 91 isn't a prime. It's 7 times 13. So it can hardly be a counterexample to this statement. It doesn't even fulfill the first part of it. Okay, so we can discard 2. So now we're just left with 1, which is a statement, two statements really. 10p squared plus 1 and 10p squared minus 1 are both prime when p is an odd prime. Now, we only have to find a counterexample to one of those two. So let's look at the first one, 10p squared plus 1. Well, 91, can it be written as 10p squared plus 1? Well, yes, it can. If 10p squared plus 1 is 91, 10p squared is 90, p squared is 9, so p is 3. Now that is an odd prime. So I have an example here where we have an odd prime put into this formula, returning a non-prime, where the claim is it'll produce a prime. We don't have to worry about this one. We've disproven it for this one, so we have a counterexample now for 1. So it turns out that the answer is B. It's a counterexample to just statement 1. Okay, another TMUA question. We've got 5 values here next to A, B, C, D, and E. It's simply which one is the smallest. Okay, so pause and have a go yourselves. Okay, now you should know the relationship between logs and indices. So log to the base 2 of 4 is 2 because 2 squared is 4. And log to the base 2 of 8 is 3 because 2 cubed is 8. So we've trapped the first one between 2 and 3. Okay, let's look at the second one. Again, fairly straightforward arithmetic, really. Okay, and we end up with 8 over 3. Okay, so again, somewhere between 2 and 3. Very difficult to distinguish between A and B, which is the smaller of A and B, at the moment anyway. Okay, so let's look at C. Yep, pi over 3, a little bit over 1 because pi is 3.1415, etc. So 2 to the power of pi over 3 is a little greater than 2. Now my money would be on that being the smallest of those three, but we're not sure of that. But again, it's between 2 and 3, isn't it? Okay, now we've got some surds to fiddle around with now. In D. It's quite a lot of work here. So we've got the binomial expansion first. Okay. Once we tidied that up, we get a fraction with an irrational denominator. So probably it's best to rationalize the denominator. Okay. Usual method. You're going to multiply the top and the bottom by 5 root 2 minus 7. 5 root 2 plus 7 rather. Anyway, the tidying up's been done for you there, and you get 5 root 2 plus 7 over 4. Now it's not obvious what's going on there, but as it suggests, root 2 is clearly bigger than 1, so this number is bigger than 3. So we can ignore that one basically. D's gone. We've got 3 of them between 2 and 3, and D is just too large, so we're going to ignore that one. Okay, so let's look at the final one. Okay, now you have to know your trig ratios, the exact values, very well. It's in radians. Now you may not have come across radians, but hopefully you picked them up through these Sump lectures. So pi over 4 is 45 degrees. Okay, remember 2 pi is 360 degrees. Pi over 4 is 45 degrees. You should know sine of 45 degrees. Okay, it's 1 over root 2. So anyway, square it, times by 4, and we get 2. So we've got the 5 cases rather now. Let's just look at each of them. Okay, first 3 are all between 2 and 3. We can ignore D, as we've said before. It's bigger than 3, so it looks like it's going to be E. Okay, so another TMUA question. They tell you you've got an increasing function. It's about an area underneath this increasing function. We denote that by R. Okay, it tells you the order of the A and B, A being smaller than B. It then defines a new function and asks you what the area under this function between A and B, how it relates to the original one. Okay, so have a read through the question, pause the video, have a go yourself. Sketching a curve is going to be the obvious way to do this, but have a go anyway. Okay, so we start at the bottom with the original curve, and we notice that f of b is simply the y value when x equals b. So if you've got g of x is f of x plus 2f of b, we simply have to move the whole curve upwards by twice this f of b. So we've done that diagrammatically there. Okay, so the whole curve gets shifted upwards by 2f of b. Now we want to know the area underneath it, so we've got this whole area here, and of course the shaded area is just R, it mimics R, and we've got to add in this rectangle. Now the rectangle has a base, b minus a, and a height, 2f of b, so the area is clearly b minus a times 2f of b. Then, if we add that to the original R, we get one of our choices here on the right. And the one we get is this one here. R plus 2b minus a f of b. So B must be the correct answer for this one. Okay, another one of these TMUA questions about counterexamples. You have to read them very carefully. So the statement is, if f of x is an integer for every integer x, then the derivative f dash x is an integer for every integer x. Now, which one of the following is a counterexample to that? Okay, so there's 4 options given there. Okay, now the easiest ones to get rid of are any that don't produce integers anyway. The f of x don't produce integers because we can ignore them. That's the first part of the statement. And if they don't even produce integers there, we can safely ignore them. So let's have a look. Well, it turns out that a and b can both easily produce a non-integer. Remember, you can put any integer, and I've chosen 0 and 1, and I get a non-integer out. So we can safely ignore both of those. Now, we haven't shown yet that c and d do always produce integers, but if you try quite a few values, you'll find that they seem to be producing integers all the time. So whatever value of x you put into either rows, it does seem to always produce an integer. And in fact, we're going to prove later that they do always produce integers. But at the moment, let's just say they're the only 2 we need to concentrate on because we've got rid of the first 2. Okay, well, let's look at the f dash x bit then. It's supposed to be producing an integer for f dash x, so let's make the assumption that both c and d always produce integers for f of x. Let's see if we can find f dash x's that don't produce integers. Okay, there they are, and there are the derivatives. And without much work, you can see if you sub 0 into c, you do get a half. Now at this stage, if you got this far in the test, you could just pick c, because there's only, they say which one, so we know there's only one answer. So you don't really have to prove for the test that d always produces a integer. And anyway, it's meant to be a counterexample, so that's not the point. But really, we should be showing, if we're doing this correctly, that f of x in both c and d always produce integer values. We can sort of assume they do for the test because there's only one option anyway. But let's have a look. Okay, so let's look at c and d in a little more detail. What we're going to do is factorize them out, or in particular, we're going to factorize out the numerators. Okay, so I've factorized out the numerator for both c and d. And what I hope you notice is that when you factorize them out, I've taken an x out first. Oh, and a point here, you've got a cubic. How do you factorize a cubic? Well, you look for roots, make it equal to 0, and one root of that is minus 1. Minus 1 cubed plus minus 1 squared plus minus 1 plus 1 is 0. So x plus 1 is a factor. And then using long division or whatever method you've learnt, if you divide that by x plus 1, you get x squared plus 1. So that factorizes to x plus 1, x squared plus 1. The second one is actually slightly easier. You take an x squared term out, and you're left with x squared plus 2x plus 1, which factorizes to x plus 1 squared. So there are the 2 functions, or rather the numerators of those functions. And let's have a look at this one first. It's got an x and an x plus 1. So clearly those are consecutive integers. So a 2 and a 3, or a 7 and an 8, or 103 and 104. Now one of those 2 must be even. We don't know which one it is, but one of them must be even. So therefore there's an even number as part of this product. Okay, so it is divisible by 2. So we do divide it by 2, we'll still get an integer. Okay, so there's a factor of 2 in here because one of these 2 is even. Okay, so therefore when we divide by 2, we still get an integer. So in fact, for c, f of x does always produce integers. And let's look at d. Well, d has this x plus 1, it's repeated. So there's an even and an odd mixed in there. We don't know which is which. But they're both repeated, so there's certainly 2 even numbers in there. Now, if you've got a factor of 2 twice, 2 even numbers, then you'll have a factor of 4 as well. So it turns out that this, when divided by 4, still gives an integer. Okay, because there's a factor of 4 in there to begin with. So actually, c and d do always produce integer values for any integer value of x. So we need that for completeness. However, in the test, you can skip this stage. Okay, so for the last question, we're going to do a long question from MAT. It's 2010 question 5, and it concerns dates. Now, the dates are written in the sort of standard form, day, month, year, digits like this. So, for instance, the 23rd of May 2013 would be 23052013. So we have to include zeros. In particular, it concerns those dates which contain no repetitions of a digit. Here's one, no digit is repeated in that date. Whereas for this one, a digit is repeated. In particular, 7 is repeated, and in fact 1 is repeated. But we'd only need one repeat for it to fail. Okay, so we're particularly interested in dates which have no repetition of digits. We're going to use what's called the Gregorian calendar. You may not realize you're using that. It's the standard calendar we tend to use. So there's the definition of the Gregorian calendar, but it's the calendar you use. Okay, so you're allowed to use leap years if you want. You can have the 29th of February as one of your answers. Just a reminder again of the form that we're going to have our question in, or rather the years, the dates are going to be written in. And there's the first question. Show that there is no date with no repetitive digits in the years from 2000 to 2099. Just highlight again the way you have to write the dates. Okay, and freeze and have a go at that one first of all. Okay, so let's consider dates of this form. Now notice we've got the 20 here because we're going from 2000 to 2099. Now I've used up the 2's and the 0's. So if we look at the months, M1 has to be 1. Remember, M1 can only be 0 or 1. 0, for instance, June, 06. 1, for instance, November, 11, yeah? So we've used up the 0, so it's got to be 1. But if the first one's got to be 1, so we're talking about October, November, December, then the second one, the M2 must be 0, 1 or 2. As I said, October, November or December. But the problem is, we've already used up the 0 here. We used up the 1 just now, and we've used up the 2. So there's no possibilities. We've exhausted them all, so there can't be any dates that fulfill those criteria. Okay, let's look at the next part of the question. So part 2, what was the last date before today with no repetition of digits? Explain your answer. Okay, well we've already cleared out the whole of the 21st century, so we've got to go back into the 20th century. So it's going to take this form. And we want the years to be as late as possible. So we've used up 9. So we want 8 and 7, slot those in. So I think we'll get 1987. Yep. Okay, now let's go to the months next. Now we've already used the 1 up. So we can't have a month, October, November, December. So that's going to have to be a 0. And then we want the next highest number still left over, which is a 6. So we've got a 0, 6. And tracking through, we've used up 198706. What's left?
So 25 is the highest we can go. We can't use 3 because we would have to put in a 0 for the 30th of June, and we've already used the 0. We also can't use 6, 7, 8 or 9, so 25th is the last possible date.
The latest date is the 25th of June 1987. Okay, so a more difficult question. When will the next such date be? And explain your answer, of course. Okay, now we can see that it's going to look like this. So that's the first go we'll have. It doesn't work in the 2000s, so let's try the 2100s. We'll try the 21 here and see what happens.
Well, unfortunately, that means that M1 has to be 0. We've already used up the 1, and M1 can only be 0 or 1. But D1 can only be 0, 1, 2, 3, and 0, 1, 2 have already been used. But if D1 was 3, then D2 would have to be 0 or 1, and they've already been used up, so that's no good.
So let's try 22. Clearly, no good, we've already repeated a digit. Okay, so we can't do that. Okay, let's change it to 23 now. We've gone forward 100 years. And what happens now? We've used up a 2 and a 3.
So M1 can be 0 or 1. Let's try 1. So M2 has to be 0. It could have been October, November or December, 0, 1 or 2. But we've used up the 1 and the 2, so it has to be 0. Now look at the days. The days go from 0, 1 up to 31, and we've used 0, 1, 2 and 3, so there's nothing left. Okay, so let's try
1 is 0. Now if M1 is 0, we do have a space for the first digit of the day, and it has to be a 1. Okay, remember it goes from, the days go from 0, 1 to 31. We used up 0, 2, 3, so the only thing that day 1 can be is 1. Right, now we're getting there now. We had the 2, 3, we had the 1 and we had the 0. I've put in 45 because we want the years to be as low as possible using any digits we haven't used. So 45 would be the next two. That would be fine. Now we want to use the next lowest digits to fill in the other two. And with a bit of thought, we can put 6 and 7 in. It's better to have the month as 6 and the day as 7, or the digit as 7 to make a day of 17. So 17th of June 2345 will be the next such date. And finally, part 4. How many such dates were there in the years from 1900 to 1999? And again, explain your answer. Okay, so we're going to look in the 20th century, so years beginning 19, and let's see what happens. Well, we've used up the 1, so M1, the first digit of the month, must be a 0. So therefore, day 1, the first digit of the days, has to be 2 or 3. Because remember, days go from 0, 1 up to 31. We've used up the 1, we've used up the 0, so they've got to be a 2 or a 3. Okay, so let's try it out with a 3. If day 1 is 3, day 2 doesn't work out, does it? Okay, if day 1 is 3, that means it's the 30th or the 31st. And we've already used up the 1, so that doesn't work. Okay, so it must be the other option, which is that D1 is 2. So we must start off on the 20th of something. Okay, so there's the basic idea. It's the 20th of 0 something, 19 something something. Okay, right, let's analyse that in a little more detail. Okay, so this is the form we're left with, the 20-something of O, so anything except October, November, December, 19-something. Now, which digits do we have left to insert into those spaces? Three, 4, 5, 6, 7, 8, and it turns out if you think about it, we can put them anywhere we want in there. So there's 6 digits that we can insert in any one of those 4 slots. So we can fill in the first slot with any one of 6, the second slot with any one of 5 because you've used up one of the digits, the third slot with any one of 4, and the fourth slot with any one of 3. So in total we get 6 times 5 times 4 times 3, 360 different possibilities. So there are 360 dates in the 20th century which don't repeat their digits. Okay, well, thank you for listening. That's the end of this lecture on MAT. I know a great deal of it's TMUA, but it's all very good practice. And remember, the main thing is with these is, as I said, the practice. You've got to do lots and lots and lots of past paper questions, okay, to get used to the sort of standard. It is higher than that in AS and A2, but you don't require any more mathematical knowledge, really. You just have to learn a few more tricks and think about things a little more deeply. Okay, so good luck with that over the summer, and bye for now.